Welcome back, everyone. In this video, we're going to look at how the Vesper theory explains why molecules take a three-dimensional shape. We're going to use the Lewis structure of a given molecule in order to determine what physical three-dimensional shape it should take. So up to this point, when we've looked at Lewis structures, we've tended to draw them as flat molecules, just out of sake of convenience. But it turns out that molecules actually have a three-dimensional shape. And using the valence shell electron pair repulsion model, or VESPR, we can predict the actual shape that a molecule will take based on its Lewis structure. And this has important significance for understanding how chemicals behave the way that they do. The term that we like to use in chemistry is that structure determines function. And so the shape of the molecule is going to affect its properties, which will affect how it reacts with other molecules. So when we look at carbon tetrachloride, instead of being a flat molecule with bond angles of 90 degrees from each other, it's actually three-dimensional and has bond angles of 109.5 degrees from each other. There are three main concepts that we need to understand for the VESPR model. The most important is that electrons want to stay as far away from each other as possible. And this makes sense, hopefully, because when we think about electrons interacting with other electrons, we know that they will repel. And so the shapes that molecules take is going to be whatever shape gets the electrons as far away from each other as possible to minimize the electron-electron repulsion. In addition, we also need to recognize that lone pairs take up more space than shared pairs. We'll take a look at that in more detail in a little bit. And then finally, if you have multiple bonds, a double bond or a triple bond, then this also takes up more space than just a single bond. So let's begin by talking now about what we call an electron domain. An electron domain is a region of space that has a high probability of electron density. This is where you might expect to find electrons. Each bonding region is an electron domain. And this is independent of the bond order. So single bonds, double bonds, and triple bonds all make each one electron domain. Unpaired electrons also consist of an electron domain. And this could be whether you have a pair or a single electron. That's one electron domain. Likewise, lone pairs of electrons are an electron domain. So these 2 points here are essentially referring to just having a single electron versus a pair of electrons. So, for example, if we look at carbon tetrachloride, and we want to count up the number of electron domains on the central carbon, we see that there are 4 domains. The carbon has a bonding region here, a bonding region here, here, and here. 4 total domains. Boron trifluoride has 3 electron domains, has 3 bonding regions. What about the central oxygen in ozone? This also has 3 bonding domains. It has a domain here, a domain here, and a domain here. 3 total electron domains. If we wanted to talk about one of the exterior elements, let's say one of these fluorines, this fluorine also has 4 electron domains. 1 for each set of lone pair electrons, and then 1 for the bond. So another way of talking about these electron domains is what we call the steric number. So the steric number for a given element is the total number of electron domains that it possesses. Let's practice. How many electron domains are around the central chlorine in ClO2? Pause the video and try this on your own before watching the solution. Welcome back. So to find the number of electron domains, we need to identify what types of domains there are. Each bond is one electron domain, keeping in mind that a double bond still counts as a single domain. So we have two sets of bonds, two domains. Each unpaired electron is a domain, and each pair of electrons is a domain. That gets us a total of 4 electron domains. That would mean then that the steric number of chlorine is 4. So the steric number, or the number of electron domains, is going to determine what we call the electron domain geometry. As the name suggests, this is the geometry, the physical arrangement of the atoms with respect to each other. And again, we're going to get the geometries that best minimize the repulsion between the electrons. So because the domains around the central atom repel each other, they will repel each other and spread out. But because they are bound to the nucleus, they must stay as close to the nucleus as possible while still maximizing the distance from each other. So if you have a steric number of 2, this is what we call a linear electron domain geometry. A steric number of 3 is a trigonal planar electron domain geometry. And notice in both of these cases, the geometry is still 2-dimensional. It's still flat. However, as soon as we get to 4 domains, this now gives us a 3-dimensional shape, a tetrahedral shape. 5 domains is a trigonal bipyramidal, and 6 domains is an octahedral. So we're going to take a look here at what these names mean. But for the most part, they make intuitive sense once you know what a given shape is. For example, a triangle has 3 corners, and if we take a triangle in a plane, then we get the trigonal planar shape. Let's now actually move to the trigonal bipyramidal because it's related. So a trigonal bipyramidal, notice we have a trigonal base for our pyramid, and that there are 2 pyramids. Hence the term trigonal for the base and bipyramidal because there are 2 pyramids. But what about tetrahedral and octahedral? Well, to understand why those are called what they are, you need to understand what is a tetrahedron and what is an octahedron. Tetrahedron is similar to it looks like a trigonal pyramid. However, the center of it is raised up. A tetrahedron is a polyhedron that has 4 faces. And when you take a look at the number of faces that you would make on a tetrahedral shaped geometry, we have 4 faces. Likewise, an octahedron is a polyhedron with 8 faces. So notice here we have a square base and we have 4 faces for each pyramid. And on the octahedron, we're going to have a square base and then 4 faces for each pyramid. Hence the name octahedral and tetrahedral. So to recap, we have here the electron domain geometries, what we call the canonical geometries, or the canonical shapes. You are expected to be able to determine for any molecular formula what the electron domain geometry is, as well as talk about the angles between the elements. So notice when we have a linear structure, the farthest they can be from each other is 180 degrees. For trigonal planar, those bond angles are 120 degrees. For tetrahedral, the bond angles are 109.5 degrees. for a trigonal bipyramidal, we have two sets of angles. There are the angles that go between the what we'll call the equator and the axes, the north or the south pole. Those are 90 degrees. And then within the equator, the equatorial atoms, you have bond angles of 120 degrees. For the square or for the octahedral shape, those all have bond angles of 90 degrees. And so you need to be able to determine from the molecular formula, the Lewis structure, the geometry, the name for that geometry. And so some examples of ones that would follow those trends are given here on the right. Now let me say a word about this notation here. A, in this case, refers to the central atom. X refers to the number of bonded atoms. And for our purposes, what those elements are could be the same or they could be different. So you could have BEH2, or you might have BEHF, which would look like the following. Either way, it's going to take a linear electron domain geometry and have bond angles of 180 degrees. Similarly, you might have PF3Cl2. There's still 5 atoms that it's bound to, and so it takes on the same overall shape. All right, let's close out this video with a little bit of some practice. So what I would like you to do is pause the video and try to determine the electron domain geometry for the central atom of each of those molecules that are shown below. Welcome back. So, what did you get? Carbon dioxide. This has 4 valence electrons plus 12 from the oxygens. That makes 16. When we draw the Lewis structure, we see that we have carbon with the two double bonds to 2 different oxygens. This then has 2 electron domains, and so that's going to be linear. For water, when you drew out the water, you should have gotten something like what's here on the screen: oxygen with single bonds to 2 different hydrogens and 2 sets of lone pair electrons. This has a total of 4 electron domains. Something with 4 domains is tetrahedral. I3 minus. This is a string of iodine atoms bound to each other, and we have 3 sets of lone pair electrons on the central iodine. That means that the central iodine has 5 electron domains, and this would be trigonal bipyramidal. Boron pentafluoride would give you this structure. Note that it has a single set of lone pair electrons on the bromine in addition to the 5 bonds. This means we have 6 electron domains, and this would be octahedral. Ozone ends up with 3 electron domains on the central oxygen. 3 electron domains would be a trigonal planar arrangement. Now, if you struggle to draw the Lewis structures, you need to go back and review the earlier videos from Chapter 7 looking at how to draw a Lewis structure. Okay, that's it for this video. Thanks for watching. Have a wonderful